Welcome. Let's take a look at lesson 11.6, which is hypothesis testing. But before we do so, let's kind of review what we just learned about with confidence intervals. Number one, a random sample of 300 airline passengers show that the average travel time to their destination was 3.45 hours. Assume that the standard deviation for the previous studies was 1.15 hours. Find the maximum error of estimate given a 99% confidence level. Then create confidence intervals for the mean travel time of all airline passengers. So what I'm going to do is I'm going to go over to our statistics calculator that I've created. We're going to go to confidence intervals and type in our information. We know the mean or assumed mean is 3.45 hours. The standard deviation was 1.15 hours. We want a 99% confidence level, which means alpha is 1 minus that 99%, which would mean 0.01. Now, so here's how I'm getting this. The alpha is always 1 minus that confidence level amount, which is 99%. So you subtract from 1 or 100%, 99%, and we get 1%, which is the same thing as 0.01. So that's my A here. And so let's see here, number of samples. We weren't given any certain number of samples here unless, oh no, here we are, 300. So we're looking at 300. I'll scroll down here. There's my maximum error. It's 0.17. So it looks like B is going to be the correct answer. And if I wanted to see the picture here, don't I have a picture? I guess I don't. The confidence interval would span from 3.28 to 3.62. 3.28 to 3.62. So it is correct. B is the correct answer here. And you can go back through and look at the formulas, how we come up with this. But for the maximum error, if you're dealing with more than 30 samples, you'd be using the normal distribution. You would take your Z score value that we get from the quantile function divided by the standard deviation of 1.15, excuse me, times that standard deviation divided by the square root of the samples, which would be square root of 300 there. So the Z value for the 99th percentile multiplied times 1.15 divided by the square root of 300. And that's how we got that 0.17 right there. Okay, and number two, in a random sample, let me explain some of this too. What we're saying is we can say with 99% confidence that the true mean is somewhere between 3.28 and 3.62. All right, so that might have been the samples mean. We can say the true mean, if we expand all the way out with 99% confidence, would be between those two numbers. Number two, here a random sample of 20 high school seniors. The average time spent watching television each week was 8.7 hours, with a standard deviation of 2.4 hours. Estimate the mean number of hours spent watching television for all high school seniors using a 90% confidence level. Okay, so here we go. This time I'm dealing with 20, which would mean I'm not going to use the Z-score value or the normal distribution. I would use the T distribution because I'm less than 30. The mean here was 8.7, I believe, 8.7 hours with a standard deviation of 2.4. So given this information, the maximum error is going to be calculated using the T-score value, if you will. The 99, oh wait, I'm at 99 percentile. We need to go to 90. Let me change this. Let's change your number. So I go to alpha, and I'm going to say 90 percentile is 0.10 or 0.1. The way we would get that is we would say alpha here would equal 1 minus 90%, which is 10%, or you can rewrite that. And like I was saying, A would be equal to, come on now, 0.1 or 0.10. So that's my alpha there. And when I come down, my T-score value for the 99th percentile would multiply with the standard deviation of 2.4, and then you would divide by the square root of 20. And we'd get this 0.93 if I round. So 0.93 is the maximum error, and the confidence interval would go from that 8.7 minus 0.93 and plus 0.93 to get those two values, which looks like to me 0.77 and then 9.63 would be, the correct answer would be A here for number two. All right, as I said, today with 11.6, we're going to check out hypothesis testing. So you can open up this calculator, scan that QR code right there. It'll bring you to your calculators and choose the AP statistics near the very bottom, and we'll be good to go. The first thing we need to talk about is this thing called the null and alternative hypothesis. So when we come up with a hypothesis, we're going to test something we believe to be true. And the null is always going to be the hypothesis that includes an equal sign of some sort. So we might say, hey, I believe that, and this is how you represent it. Null would be the capital H with the little 0. That's the null hypothesis. We might say we think that the mean of some sample is 5, equals 5. And an alternative in that case would be, and you write this H with a little a, H hypothesis, alternate hypothesis would be that A does not equal 5. Okay, so the null will always have an equal sign, no matter if it's with an inequality or if it's just truly equal. So we might say another one might be that we believe that the mean is less than or equal to 7. That would be the null. So the alternative hypothesis would that be that the mean would be greater than 7. So the alternative never has an equal sign. Whereas, and let me give you one more just for good measure. We could say that maybe the initial or the hypothesis, the null hypothesis, is that the mean is greater than or equal to 3, which would mean that the alternative hypothesis or the alternate would be that the mean is less than 3. Notice each of these, the null, hypothesis can be equal. Alternative hypothesis cannot be equal. Cannot be equal. Okay, so just so there's some rules so you know about this. There's the null. The null is represented by HO. Here's the alternative, HA. Okay, and so let's get started here on number 1 here. And there's a lot of info I might use today, some vocabulary. It says, for this statement, write the null and alternative hypothesis. State which hypothesis represents the claim. A restaurant owner claims that it will take no more than 12 minutes, so that it could be equal to 12 or less than 12 after ordering for meals to be served. So the no more than means it can be equal to. So this, since it can be 12 or less, we would say it's the null hypothesis is that it'll take 12 minutes or less for meals to be served, which would indicate that the alternative hypothesis is that it takes more than 12 minutes for meals to be served. So there's the mathematical principle here. Now let's talk about this word claim. The claim is the belief. And so the null hypothesis always has the equal sign. Alternative never has the equal sign. The claim goes with the one that we believe to be true. It says a restaurant owner claims that it'll be taking no more than 12 minutes. This is the claim here. He's claiming this one. So in this particular case, the claim happens to be the null hypothesis. It won't always be that way. Okay, so that's part A. Let's take a look now at part B. It says, new problem starting here. A company claims that the light bulbs last more than 1,200 hours. So this time we're saying more than. That means it's not equal to, but more than. So this will actually become the alternative hypothesis. Is that if it's greater than 1,200 hours, that means the null hypothesis must be that it's less than or equal to 1,200. The particular, on this problem, the claim is this. So the claim over here would be the alternative hypothesis. So sometimes we'll be claiming the alternative. The alternative is not going to have an equal sign. The null will have an equal sign, if that makes sense. Let me make sure I arrowed over here that this one would go this way Okay. And this one points to the alternative. All right, and now let's look at part C here. It says a reviewer claims that she averages 17 reviews published per month. So that is an equal claim. We're saying she averages 17 reviews. She averages 17, exactly 17. So this is going to be the null hypothesis. The null is that she reviews exactly 17. The alternative hypothesis, however, would be that she does not review 17 per month. What is the claim? The claim is this statement here, that she reviews 17. That's the claim. And we could test from there. Now with that information, go ahead and try example 1. Pause the video if you need more time. And I just realized one thing I need to correct here is on all of these, I should be saying the mean. We're testing the mean. So if I really wanted to get all this correct, I would need to go back and edit these. So let me go ahead and do that now. HO is you're testing the mean, and then alternative hypothesis. Again, you're testing the mean. On each one of these, it looks like I did that correct. So let me correct that there so there's no misunderstanding. And formatting. And finally, one more time. There we go. And so here's yours now. Example 2, test of the significance. It says if the alternative hypothesis we're looking at is that the mean is less than k, the hypothesis test is a left-tailed test. We want to find out that if the value falls within what we call the critical region over here, it'll be shaded on the left. This is if the mean is less than k. So that would mean the null is that it's greater than or equal to k, which would be all of this area. On when you test if mean is not equal to k, that means k would be represented by the inner unshaded region. The critical region would be each of the outside, which is alpha divided by 2 for both sides. So whatever your significance is, you divide it by 2 for each side. And finally, if the alternative hypothesis, the mean is greater than k, you'd be looking at the right side, where 1 minus that alpha represents the larger percentile area of the null hypothesis, where this would be represented the alternative hypothesis. Now, I happen to have this same chart. If you go to hypothesis testing, I kind of wrote it out here as a table so you can see over here each of the value and compare to see what it should look like, okay? Now, the calculator should do this by itself, and that symbol right there means not equal to k. So this is the 3 situations right here. The calculator should do a lot of this for itself, but it's just going to help you out. All right, so let's solve some of these problems. And here's some tests over here we've done on example 1, step 1, and now we'll come up with the other 3 steps here as we go. So it says first, in an advertisement, a shipping company claims that packages will be delivered in less than 5 days. So let's first start with our hypotheses here. The null, remember the null hypothesis always is the one with the equal sign. So mean is going to be equal to some value. It says here the shipping company claims that the packages will be delivered in less than 5 days. That does not mean equal to. Less than means less, not equal. So that means the null hypothesis would be that it's going to be greater than or equal to 5 days. The alternative hypothesis happens to be the claim that, the mean is going to be less than 5 days. This will happen to be the claim here. All right, now with that being the claim, now let's put in our data and see what we can come up with here. So that's step 1, if you will. There's step 1. Now it says a random sample of 40 delivery times. So that's the number of samples here. We have n equals 40. Has a sample mean of, and I'm going to say that, I'm going to write this as mean of the sample. The mean of the sample is 4.9 days. And a standard deviation of 0.2 days. So standard of the sample is equal to 0.2 days. Is there enough evidence to reject the claim at alpha being 0.05, which is the standard term? This is like a 95% confidence, if you will. So I'm going to come up here. I have my alpha at 95%, but I'm not going to have two tails in this one, because when I'm looking at, go to this chart here, the mean is less than, it should be one-tailed, and we're going to be looking on the left side. So we'll see how this works. I'm going to change this to one tail. We're looking on the left side. So what we know about this the problem here is that we're testing that the null hypothesis, the equal to number, the number that can be equal to, is 5. The number of samples was 40. The mean of the samples was 4.9. The standard deviation in the samples was 0.2. And so what's going to happen is it creates this test statistic. Okay, on this problem, it's a t statistic because we have a less than on the samples, or I'm sorry, the t statistics is, there's a formula for this, and what it does is it takes the mean of the samples minus the mean of the population, and it divides that by the standard deviation of the samples divided by the square root of the samples, and we get this number. Now, this number happens to fall, it's kind of telling you where the number is because it falls less than the z number. That's the z number for, that's like the quantile function for 0.05. Because it falls in that, it shades that region. Now, I have a little visualization. Let me show you. I think I put it under alpha visualization. Yeah, there we go. Given a 95%, what it would look like, and we're looking at the left tail. Let me zoom this in. There, you see how this blue shade is shading this portion of the graph here. You can see that this test statistic is falling into the shaded region there. And because this test statistic is in this critical region, we would say that this actually is in agreement with the claim, but it fails the null hypothesis. So the null hypothesis would be, we would fail this, but we would actually assess that the claim is correct. Now this is where this can get a little bit confusing. So let me write down here the t statistic here, the t statistic that we get from the calculator. T statistic is going to equal, when I let me come back over here, down, where was it? Was negative 3.16. This here is the z value for alpha equaling 0.05. Okay, since that t value would be over here in the critical region, we would reject the null hypothesis. Here's how you write it. And this is a little bit confusing, but you always refer back to the null hypothesis. We would reject, or you fail to reject, one or the other. In this particular case, I'm going to reject the null hypothesis. I'm going to reject the null hypothesis, which you could have just written H0 there, because this test statistic happens to be further away from the center of this graph than, or it's in the critical region, I should say it that way. If this is 0, this test statistic, it happens to be in the critical region. For that reason, I would reject the null hypothesis, and then the evidence, there's not enough evidence to reject this claim. So you would actually not reject the claim in this particular case. We reject the null hypothesis, and the evidence, we would, based off the evidence, we would not reject the claim. So I guess I could go ahead and write that out here. The evidence does not, whoops, forgot the O, does not reject the claim, which is the alternative hypothesis. So the evidence does not reject claim. So all this here, you could write your answer either way here, but whenever you write it, and this is what I was saying, is a little confusing. is you don't always say we accept it. What you do is you either reject or you fail to reject, meaning you do not reject. So we reject the null hypothesis. The evidence does not reject the claim based upon where that t statistic was located. Now I have one for you to try here. You can pause the video, take your time, and see if it falls into this critical region or not. Example 3. A pharmaceutical manufacturer produces a heart medication in 50 milligram tablets. The quality control manager conducts a study to determine if this is true. She selects a random sample of 20 tablets that average 49.7 milligrams with a standard deviation of 0.6 milligrams. Is the difference statistically significant at alpha equals 0.05? Okay, so first let's find out what the claim is. The claim is that the heart medication is 50 milligram tablets. And so the null, that would be equal to 50. Now here's what's weird is I believe, let me check the textbook again. I think they actually say less than, but I don't agree with that on this particular problem. No, I'm wrong. The textbook does say equal to. Yeah. The claim is that the mean will equal 50. Which means the alternative hypothesis is that the mean does not equal 50. So because it's a not equal to 50, there's going to be two tails. You could fail being too small or too large. All right. And they tell us that the mean of the samples is 49.7 with a standard deviation of 0.6. Now, is this difference, and I'm just writing down these values so we can keep track of it. The mean of the population will be 50 here, and this happens to be the claim. And so that's the claim, is that it produces them in 50 milligram tablets. 50 milligram, there we go. So anyways, we're back over here. We sample 20 tablets. So that's the number of 20 samples, and we get that information. And we want to know with alpha being 0.05. Okay, so I come back to my calculator. I refreshed it so you can see this all again. I have an alpha already. It's the standard 0.05, which is 95% confidence typically. The tails, I'm going to say 2 because we could fail if it's too small or too large. That's why it's 2 tails, which, by the way, this kind of explains it in hypothesis testing. My calculator froze here. Let's see if it'll wake up here soon. There you go. If you scroll down here, you can see if the mean is the alternative hypothesis is that the mean does not equal some value, you would call it two-tailed. And so that's what I have here. And I will type in my values. We're saying the mean of the population is 50. The number of samples happens to be 20. The mean of those samples is 49.7. The standard deviation of the samples is 0.6. The test statistic is negative 2.236. Now you're going to see this falls in the critical region because that's the z value that's created at 95% with 2 tails, which means that's the z number for 0.025, and this would be for 97 or 0.975 is where those numbers come from. If you did the quantile function, that's where those would come from. For that reason, the t statistic here, we would say it fails again, or I say fails. It falls in the critical region, which means we're going to be going with the alternative hypothesis. So here, the t statistic, the test statistic, I should say, is negative 2.236, which falls in the critical region. So this is, since it's less than 20 samples, this is the t value. It's the t-score for alpha divided by 2. And this is the other t-score for 1 minus alpha divided by 2 is how you get that one. And so the reason, the numbers you heard me quote earlier, what's happening is if I went over to the student or t distribution, what we're seeing here is that a value will be calculated I don't want to go all into this, but it's that negative 2.093. You see it there, and 2.093 right here. That's where those values are. It's going off of this alpha divided by 2. And so that's the math that's occurring in your calculator. You can see this area shaded. Now, if you're wanting to know where's the whole distribution, like this has a whole distribution, you need to go to the alpha visualizations and turn that on. So on this particular case, I would turn on both the left tail and the right tail. I can zoom in. And you might look and say, well, that's not exactly equal. And that's because I made a mistake. I turned on the normal distribution. Let me fix this. I need to turn on the t distribution. So I'm going to go down because I'm less than 20 here on the samples. And so I'm going to go this value, and I need to have degrees of freedom. It's always 1 less than the samples. So 20 minus 1 would be 19. And so you can now see that this is in fact in that shaded region. So it's in that critical region, that test statistic. This should light up blue if it's ever in the critical region. That's the way I programmed it, just to draw your attention to it. So this would, what we would say is we would fail our claim. The evidence, we would reject, I should say, reject the null hypothesis or reject the claim, or null hypothesis. Which again, you could rewrite as H0. We would reject the claim or the null hypothesis in this particular problem. And I should include here based off of the evidence, based off. So we might think that looks pretty good, having a 49.7 milligram. They might say, well, that's pretty close, but with that standard deviation, it's we can't state that with confidence, 95% confidence that we will be giving people 50 milligrams. That means we fail to accept, we don't fail to accept. We would reject the claim based off the evidence that the null hypothesis is true, that the mean is equal to 50. So with that piece of information, I'm now going to let you try another. Pause the video if you need more time. Now, example 4. It says in biology, the average weight of an adult mallard duck in one state area is 1.1 kilograms. So it's saying the average duck is 1.1 kilograms. A researcher is concerned that ducks in a smaller region suffer from the disease and are dangerously underweight. So the claim is that they're underweight. So we could say, since the claim is that they're underweight, that means less than, we're going to say that the null, because the null is going to have the equal sign, doesn't have to necessarily be exactly 1.1. We're thinking that they're underweight, which means we could be equal to or greater than 1.1. So that becomes a one-tailed test here, and which means the alternative hypothesis is that the mean is less than 1.1. This will be a one-tailed test, and when you look at this, it will be the left tail because we're testing to see if it's less than. And the claim is here that they are underweight. So we sample the mean of the samples. And if you're going, well, what's the mean of the actual population? Where do you get that? It's from the null hypothesis, the mean that's always equal to. It's equal to that 1.1. I know it can be greater than, but the number that it could be equal to is 1.1 there. So that's what we're going off the mean of the population. Let's say we sample 45 ducks, 45, so this will be a normal distribution because it's over 30, and find that the average weight to be 0.9 kilograms with the standard deviation of 0.5. We want to determine whether this result is significant at alpha 0.05 or 95% confidence. That's another way of thinking about it. So what I'm going to do here is let me turn off these. We're not going to be using the t distribution. What I'm going to be using this time, so I'm in the visualizations. I'm going to turn on just the left tail. We only are going to have one tail on this particular problem. So I'm under the A. And now I'm dropping down to the hypothesis testing. The mean of the population we're saying is 1.1. The number of samples happens to be 45. The mean of the samples is 0.9, and the standard deviation is 0.5. And so what we can see here is this test statistic is in the critical region. So again, I will reject the null hypothesis. The evidence supports the claim. Okay, so this time the test statistic, I'll just say T statistic, is equal to negative 2.68. You can see the value. That's not the z value, that's the test statistic. Let's go T here. The z value is this number here. At 95%, that's going to be negative 1.96. I just, or wait, that might be for two tails. Let me check this. Let's go to visualizations, and it should show us what the number is. Oh, there it is. It's 1.64. So that number here is wrong. Let's change this. The z, that's the test statistic there. It should be 1.64. You might say, why is it not showing negative? Well, this one, it's the graph. Let me go over here. You can see it's symmetric. And I just program mine to always give you the positive number, so it just be the negative on there. That's the z value. The test statistic happens to be negative 2.68, which means it fails. It's a further left. It's in that shaded region. Now I'm going to come back over here. This p-value. Here's the p-value, and the p-value, a lot of people argue on whether it's important, whether to use it, anything like that. I programmed it in my calculator, and it says that the number is 0.003. And so you fail, or you reject, if this number is less than alpha. If this number was greater than, you would accept it to be true. But because this number is smaller than that 0.5, since, let me write that out here, since the p-value is less than alpha, you reject the null. I'm just going to put H0 this time because I'm using all the other symbols. Okay, so coming back and writing it the way we have been writing it in full sentences here, we would reject the null hypothesis. The evidence supports the claim. Or I should say, does not reject the claim, because you don't really accept anything. You either reject or do not reject. So the evidence does not reject the claim, which happened to be the alternative hypothesis. Okay, and so that would be our answer here. And so that's what that p-value is right there. Now, I have a DOL for you to try. Try DOL number 4. Pause the video if you need more time. And looking at the answer choices, it seems I had an error. I just corrected it so that now you should have a correct answer there and 4 different answers as opposed to 2 that are doubles and these 2 doubled up. So choose wisely.